Welcome. In this unit, we're going to explore a precise and powerful way to define software architecture and understand its most important properties. Let's start by refining our definition of software architecture. A common but insufficient way to think about it is as the system's early or major design decisions. The problem is, this isn't always true. Architectural decisions aren't always made early, especially in agile development. Plus, lots of non-architectural decisions are also made early. And figuring out if a decision was major is something you can often only do with the benefit of hindsight. So, we need a more precise and useful definition. Let's define software architecture as the set of structures needed to reason about the system. These structures are made up of software elements, the relations between them, and the properties of both those elements and their relations. This new definition has some direct and important implications. The first is that a system's architecture isn't just one thing. It's a collection of software structures. You can think of a structure simply as a set of elements that are held together by some kind of relation. No single structure can be called the architecture. Instead, any given system is made up of many different structures, which we can group into three main categories. These three categories help us organize how we think about a system. First, we have module structures. These are static, meaning they describe how the system is partitioned into implementation units, which we call modules. They are the basis for assigning work to teams. Second are component and connector, or C&C, structures. These are dynamic, describing how elements interact with each other at runtime to get the system's work done. And third, we have allocation structures. These describe how the software maps onto its broader environment, like the hardware it runs on or the teams that build it. Let's look closer at module structures. These are the static blueprints that divide a system into implementation units, or modules. This division is what allows us to assign work to different programming teams. For example, you might assign one team to work on the database module, another team to the business rules module, and a third team to the user interface. The main focus here is on how the system's functionality is broken down to make development manageable. Some specific examples you might be familiar with include the module decomposition structure, which shows how large modules are broken down, class diagrams from object-oriented design, and layered architectures. Next up are component and connector, or C&C, structures. Unlike module structures, these are dynamic. They describe how different elements interact with each other while the system is actually running to perform its functions. The elements in these structures are called components, and they are always runtime entities, not static code units. For instance, a C&C structure might show how various services communicate with each other and with the system's infrastructure, including details about how they synchronize their actions. It's important to remember that these runtime components are the compiled result of the code that was organized into the static modules we just discussed. Finally, we have allocation structures. These structures are all about mapping the software to its wider environment. This environment can include organizational contexts, like who builds what, developmental contexts, like how code is managed, and execution contexts, like where the code runs. For example, an allocation structure might show which modules are assigned to which development teams. Or it could describe how modules are placed in a file structure to manage integration and testing. Another common example is a deployment diagram, which shows how runtime components are placed onto physical hardware for execution. Now, for a critical point. Just because you can describe a structure doesn't mean it's architectural. A structure is only considered architectural if it helps us reason about a system property that a stakeholder actually cares about. This could be functionality, availability, modifiability, performance, or something else. For example, a structure defined as the set of all source code lines containing the letter Z, ordered by length, is not architectural. Why? Because it doesn't help you reason about any meaningful attribute of the system. It's a structure, but not an architectural one. The second implication of our definition is that architecture is an abstraction. When we define architecture using elements and their relations, we are deliberately leaving out information. Specifically, we omit details that are purely internal to an element and have no effect on anything else in the system. Architecture cares about the public face of an element's interface, the details that influence how elements are arranged, how they interact, and how they compose. Private implementation details are not part of the architecture. This level of abstraction is absolutely essential for managing the complexity of any modern system. A third implication is that every single software system has a software architecture. This is because any system can be described as being made of elements and relations to support some kind of reasoning. Even in the most trivial case, you could describe the entire system as a single element. That's not a very interesting architecture, but it is a valid one. But here's a key distinction. The existence of an architecture is different from the existence of its representation, like its documentation. A system still has an architecture even if the original designers have left, all the documents are lost, and all you have is the running program. This really highlights why documenting your architecture, and sometimes reconstructing it from what's left, is so important. Fourth implication is that architecture includes behavior. An element's behavior is considered part of the architecture to the extent that it influences other elements or the system as a whole, and can be used to reason about the system. This is why simple box and line diagrams aren't, by themselves, architectures. When you look at a box labeled database, you might imagine what it does, but that behavior isn't actually represented in the diagram. The drawing only starts to become an architecture when that imagined behavior, which relies on information not present in the drawing, is taken into account. So, if an element's behavior affects other parts of the system or its overall goals, that behavior must be considered and documented as part of the architecture. Finally, our fifth implication is that this definition doesn't make a distinction between good and bad architectures. A system can absolutely have an architecture that is poorly suited for its goals. A bad architecture might prevent a system from achieving its required behavior, meeting its quality attribute goals, or having a healthy life cycle. This fact really underscores the critical need for us to perform deliberate architecture design and systematic architecture evaluation, instead of just relying on trial and error and hoping for the best.